Hello everyone. Today we will be looking at how to use the digital screen. I don't know what happened there, but we're going to be learning how to use the digital screen today. Wow, crazy, right? What a world we live in. At least we're going to learn how to use it with the CPU, because you can use it with other things, but I will not be using other things. I'm going to be using the CPU in this little tutorial. Just going to set everything up. I had like a little thing set up already, but I deleted it because people probably might want to see me set this up since it is a tutorial. I got distracted by the code. I'm debating whether I should use this or not, because I made that's like a test code I made earlier. Now we're not going to use it, but I am going to copy it just in case. In fact, I don't think we'll need anything else. Okay. So if you remember, place the CPU down. I typically get a constant value chip in order to keep it on 100% of the time. I saw in one of the in the comments that CLK stands for click, so that's interesting. That's good information. So just wire this to any value, like a positive value other than 0. It doesn't have to be 1, just can't be 0. I haven't tested it with a negative number. Here we go. Get a button that's not a toggle button, because this will be used as a reset switch. And you don't want toggle buttons for the reset switch. Alright, that's all good and dandy. I'm gonna wire you will want to wire the frequency something higher than its default value, which is I think 4,000. Don't quote me on that. I recommend this value for this tutorial. What is that? 120,000. That is a good value for this. You don't need an address bus for this tutorial. However, I am going to place one down because it lets me see whether data is actually traveling through the address, or is actually going to whatever device it's hooked up. Like it says, if you see in that little text pop up when you hover over it, it says data rate. That shows you how much data per second is actually going over the address bus, which is super useful for debugging. So I will have that there. Wire the memory bus up to there. Oh yeah, size and offsets and stuff. Ooh, that's a bad color, but the offset is 0 and the size is max. Where's the wire tool? And then wire memory 1 to the memory of the digital screen, and wire the click of the digital screen to a value. And that's how you set everything up. Okay. I'm now going to test something very quickly, just in case, because it's always good to test things before you actually try to use them. Yeah, I'm just gonna test it real quick. This should work. It's not working. It is going over. Is that that's not actually. Let's test this one. Yep, it's working perfectly. Okay. Please stop. You know what? Oops. Let me get a toggle button out actually, because I'm foolish and I wired it to be on constantly, and I'd rather it be I like to be able to turn it on or off for demonstration purposes. See, when it's off, it doesn't actually update, and then the second I turn it on, it updates again. I just want to do that so the screen doesn't get distracting. Okay. What will we be doing now? Right, I said I was going to teach you how to use digital screen. Okay, so the digital screen, like many wired tools that are compatible with the CPU or have high-speed memory, quote-unquote, which just means the CPU can use it, or it's designed to be used in that way. It has special, settings and functions that you can access with it. And I have a list of those because those settings, in order to be accessible via the CPU, have their own little specific addresses in the digital screen's memory, which means you have to send a number to a specific address in order to actually change the settings. I'm looking for it. Okay, the high-speed cheat sheet. This has all these values for all the tools and stuff. here's the one for the digital screen. You can see you have all these settings and stuff, like the color mode and things. I will be set, you know what? That can wait, actually. Well, might as well get out of the way. What's the value is the color mode at again? Oh yeah, over here. Okay, so actually I'll put that in the description. The digital screen memory addresses for its stuff. I'll put that in the description for ease of access. Okay, so I typically start my programs with two labels. INIT, which well, to me that stands for initialize. I have no idea what it actually stands for. And then I have main. Typically I have it so that things that only need to run on startup go right under initialize, and then things that loop, like the main program, will go under main. In fact, let me just jump back to main, make that an infinite loop there. What else? Right. Okay, so the digital screen has the ability to change resolution. You can change this via the memory addresses, or one of the memory addresses. I can't remember where that is now. I had it earlier. Oh wait, no, it's fine. See, this is why I copied that thing from earlier. I'm glad I did. Dang it. God dang it, I copied over it. I'm so smart. You know what, this will only take a second. I just need to find where it is now. Oh yeah, width and height, there we go. Ignore the 2000, that's okay. Actually, I should explain this a little bit. So, if you remember, the CPU's memory goes all the way up from 0 to 65535. 65535, which means 65536 is the first memory location or address 0 of whatever is actually connected to the memory bus. In this case, an address bus is connected to the memory bus. The offset is 0, and that basically means the address. The first address of the digital screen is at 35536 is the simple way of explaining that, I think. I hope I'm not skipping over too much. I can't remember what I did in my other video, what I have and haven't talked about. I mean, well, that was the hello world, and that had to use addresses and for the console screen, so I'm sure I already explained that. I had to have. But yeah, it's like the console screen from the hello world example. You send values to it, stuff shows on screen. You'll see in a minute. Now, I mentioned the resolution thing earlier. It goes up to the resolution of 512 by 512, and that's pretty good for what this is, you know, being an emulation of a screen in a game using a fake programming language. However, that is quite a lot for a poor little CPU to handle. So in order for to improve the visuals and the speed, just to get on with this, I'm going to put it to 128 by 128. That means the screen feels faster, you see more, you know, that's just me. It all compiles perfect, or assembles perfectly. Technically compiled, but I'm going to say assemble it anyways, just because this is an imitation ASM. Now what do we do first? My mind has gone blank. Come on, brain, you can do this. I should probably reset it, actually. Just, there should be a reset. Hardware clear screen. I'm going to take that value there. We're going to do a move. Like I said, first address of the digital screen's memory is this. That's why we're starting with it. And then we add the address of the reset switch, and then we move it to 1. So every time this code right here, this one line is run, the digital screen will completely blank out and get rid of whatever was on it before. which is pretty useful whenever you need to hit the reset switch. You need to have stuff disappear. What else? Right, here's the actual coding part of this. I'm going to move the address of the first memory location of the digital screen to EAX. You will see why in a minute. It's for memory access. I need that. It needs to be in a register for a loop. Sure, I could just do this. Oops. And technically that would work, but that's only for one pixel. That's only for one freaking part of one pixel. And since you need this address to change for this, it's good to have it in a register. In fact, I think that's really the only way this can work. I'm not entirely sure. I've never tried to do it another way. What else? I forgot to set the color mode. Silly me. I think I forgot to set the color mode. I'm not actually sure. Yeah, I did. Set the color mode to 1 for this example. The color mode changes how it interprets the pixel data you send over to the digital screen. So if I were because with color mode 1, it accepts pixels in the format of RGB, you know, come on, bring 255, I don't know, we're just gonna put a little label here called pixel, put a little data under it. 255, that's 1, I think that's, what's that, red, and then 255, which is RBG, is RBG or RGB? Whatever, RGB. So this is red, this is green, this would be blue. In color mode 1, if I sent these all to consecutive addresses, assuming that it's aligned properly, it would show up as a white pixel. If I changed the color mode to something else, it would interpret this data differently. Is how I can best explain it. And I'm not an expert on how the other color modes actually work, so I'm just going to use color mode 1 for this example. You guys can experiment with that on your own. In fact, I'm going to keep this pixel data here. You guys should probably do that if you're following along. It will be useful in one moment. What else do I need to do? I set the color mode, I did all that. I'm trying not to get ahead of myself, because I have to remember I am doing a tutorial here. I can't just go full on speed or as fast as I want. Is there anything else I need to do? I don't believe so. I'm doing this on the fly just so if I mess up, because I do believe if I mess up and I make an error and correct it, it'll help you guys. Because if I can mess something up, you guys are probably going to mess something up too, or at least there's the potential of that happening. And the point is to help people learn and fix problems and mistakes. Anyways, aside from that little spiel about nothing, I think that's it. I don't need to reset any registers because this only runs at the beginning of the program where the registers are already set to 0 anyway, so I don't need to set anything up, or I don't need to zero anything out. Alright. We're going to start moving the pixel data, or the color data for the pixels, into the digital screen. Crazy, right? So we're going to do move. The address, we're going to interpret EAX as an actual address, not just as a register itself. And then, so what this does is this moves the value 255 to the address of 65536 instead of actually moving the value of 255 to the register itself. So to put that in other words, EAX isn't getting this value, this address is getting the value, if that makes any sense. Now we need to do this again because that's only one part of the pixel. Since there's 3 numbers to each pixel's color data, that means one pixel takes up 3 different addresses. So there, consecutive addresses actually, and there, that should equal a white pixel, and hopefully this will actually freaking work when I put it on the screen. Please work. Oh wait. Yeah, it worked. See, there's it worked first time. There's that pixel we just sent. Very cool, very cool. And then what we do in order to just turn this into a basic loop and fill the entire screen with white pixels, we're going to add 3 to our register EAX, and it'll switch the addresses and it'll fill up the whole screen. Now let me explain something real quick, because some of you may be wondering, why did I add 3 to it instead of actually just adding 1 to move over the memory placement? Because we did this, because there were 3 since there are 3 numbers to a pixel's color value, that requires 3 addresses. And since we're filling up 3 addresses, based off of what's in EAX, we have to add 3 to EAX, so it actually goes over to the next pixel's color data, if that makes any sense. If we just added 1, like, we'd be overwriting the data from the previous pixel, and that like, it'll have no visual difference because we're writing just the same value. Or maybe it does. Oh no, it doesn't. I just didn't have the screen on. Like, it doesn't have a visual difference because we're writing all the same data, but you can see it, like, you see how it's changing colors? It's because it's like the frame of the it placing the addresses is off. You can't tell now, but it's far more noticeable when you have different color, different reds and blues and greens in the pixels. Now, I'm sure you guys want more than just a boring white color on your screen. Let's spice things up a little bit. We're not going to make things too complicated. However, I would like to add something to it. So we're going to be replacing these values. And this is where this pixel data actually comes into play. Because at first I wasn't actually using this. I just use these for, demonstration purposes. What do we do here now? I guess you're not really supposed to do this in real assembly. In fact, I don't think it would work in real assembly. Like, you can't move a memory location directly to or the memory add an address directly to another memory location. I'm pretty sure. No, I know you have to use in like a register as an intermediary, but in this case it doesn't matter. I don't think it does. Pixel, let's put it at 100. I just need to see something. Like I said, putting it in brackets tells the compiler or the CPU or the assembler, whatever you want to call it, to treat it as a memory address, and instead of actually treating it as a, you know what, you'll see. I'm pretty sure you guys get it, kind of, hopefully. Oh, it didn't work. Oh wait, no, that's just not. Oh, there we go. Yeah, okay, it worked. It worked. Then just to test it, yeah, okay, it's working. We're actually going to use the pixel data. Well, yeah, we're going to use the pixel data just to keep things simple. Oops. +1 because we want to use this one, not this one. +2 because you want to use this one, not the other two. And now it should work. Or not. Oh, that's amazing. Yeah, okay, so that doesn't work. Alright, this is fine. Everything's fine. We're gonna be extremely clever. And we're gonna move the address of this label here into another register. And then we're going to treat that register as a memory location, just like we treated the label as a memory location. And then instead of doing, actually that should work. If it doesn't, I have a fix for it. Come on, I can type. That's 1 x plus 2. Aha. Yeah, it worked. Okay. There we have it. It's still a white screen, but however it is changed, this is kind of necessary. It's not necessary, but it keeps things simple. I want to say. I feel like if I overuse a bunch of registers, this will come unreadable, or it will become unreadable and hard to follow. And I really don't want that to happen. Although I'm sure it's happened for many of you already. Because I have a feeling I'm quite incoherent right now. This is what happens when you're up at 1 in the morning, but it's fine. Alright, we're gonna turn some of these colors a different. We're gonna turn some of the pixels a different color. That's what I tried to say there. I'm gonna teach you guys new instructions. My God, what a world we live in. Okay. Random number. This sets a register in this case to a random floating point value between 0 and 1. We're going to make a random number between 0 and 255. Now you're probably wondering, how are you supposed to get a random number between 0 and 255 if it only makes a random number between 0 and 1? Well, there's a simple solution for that. What we're going to do is we're going to multiply EDX by 255, and because it's a random number between 0 and 1, it will kind of scale at different places, like so. No, that's really what it does. That's how you get a random number between 0 and 255. You get a random little floating point number there, then you multiply it by 255. Oh, and there's one more thing. We need to force it to be an integer, because I don't think the digital screen will appreciate it if you give it a number with 19 decimal places. And this little instruction here forces the register to be an integer, hence the name FINT, force integer. Now that we have our new random value between 0 and 255, we will move we're gonna move our new value to the pixel data down there and replace this value. I don't need to save it. Okay. There you go. See there, and now it's varying a lot. I think this looks kind of cool. It reminds me of like the ice texture in Minecraft, or kind of like snow. There you go. Look, it's changed. And you can do this however you want, or however many times you want. So, in fact, we're going to do it several times. There's also some more registers, like R0 and R1. And then we're going to multiply. Oops, that's just, okay, R1. These are normal, these are like general purpose registers, I'm pretty sure. Unless I'm completely misusing them. It doesn't matter. It's fine. It's fine. Just treat them as normal registers. Then you multiply those by 255. And I keep putting mult instead of mul. And then you force those to be integers as well. R1. And then you copy that. I don't think that's going to work actually, because I need to move. Is EBX being used anywhere else? Anywhere else at all? No? Okay. Sorry, like I just remembered, like we ran into this problem earlier. Doing this doesn't actually work. So we're going to replace it with EBX. And then we're going to add 1 because of the different color values. And then we're going to replace this with the other random number and this with the other random number. 79 bytes. My god, completely random. Look at that. Ow. Well, there you have it. We just made something cool. And you can do all kinds of stuff with this screen if you're smart. Like, I saw this dude on YouTube, probably a few years back now. He made an actual program that converts what was it, PNGs, or like was it PNGs, was it bitmaps? It was probably bitmaps to a format readable by the CPU. And then he programmed the CPU and game to actually load the new converted images into the digital screen. I thought it was freaking cool. I wish I could show you that, but unfortunately I haven't made a program like that. Maybe I will in the future. Probably not. Sounds like actual work. But there you have it. And of course, if you want one color to be less random, I want to say, or if you want it to be suppressed, I guess you could give it a smaller value and it'll show less. Yeah. This is actually how I made my color palette generator. I think I showed it in a video way back. It might have been that update video, or was it? It was some video. I'm pretty sure I showed it off. One of my little contraptions has a color generator, or not a color generator, but like a palette generator. I think I wrote it for the GPU. Oh well. Well, there you have it. I'm gonna play with this a little bit. Oops. Let's do that. I'd also like to point out that this is not too efficient, because to tell you the truth, I could cut this out completely and just use registers, but I feel like maybe it helps just to give a name to some of the values, you know. I think that's pretty cool. It's pretty slow though, I will say that. The GPU is very fast, or it's far faster. Maybe that'll be my next video, perhaps in like 20 years. Well, there you have it. I hope you guys learned something. I said this is going to be quick. I've been recording for like 30 minutes now. Sorry.